Okay, real quick, I did write this down wrong. Hopefully I said it correctly, but it was negative 6.75, so make sure you make that correction from the last video. Alright, we're going to look at another example. It's very similar to the last one. They give us a different f of x this time. They give us a different interval to work with, and we can see it doesn't start at 0 this time. They tell us partition subintervals to work with. And they also tell us again, like they did last time, the evaluations, when we do our f of x, we're going to evaluate at these particular values, so in our subintervals. So I'll give you a few minutes to write that problem down, and we will go ahead and just work this one through. I'm actually going to work this one without drawing the sketch of it this time, just do all the work and see how you like it. Some people prefer to draw the rectangles in and see the graph, and some people may not, so I'll just do it this time so you get a different view of it. Okay, let's just check your work so far. First of all, I'll work with my partitions. 3 minus 1, delta x sub 1 is just a partition of 2, so on and so forth. Now we see that this time they have not all the same partitions. So where in this first problem we will able to use this formula because all of our delta x just so happen to be the exact same, so we could declare our x sub k as a common 1.5 of delta x. In this particular case we cannot do that because they are not all the same, so we determine the number of rectangles 5 by how many partitions we have. 1, 2, 3, 4, 5. So now we have our partitions, our f of w sub k, and then we also have our delta x sub k. So now we're going to work with that. Now the other thing that was a little bit confusing is this is what was given in the problem. So we're going to evaluate at 1, 4, 5, 9, and 9. Yes, these are repeated, but we're going to use these exact values to check our solution. So now I want you to work on the evaluation of this Riemann sum, and then we'll check our answer. Okay, here, so we square root of x, our first x value is 1, and the width of our first partition, this is our width, is 2, so that's from right here. That's going to be our first rectangle. The second rectangle will be the square root evaluated at 4, because they told us the evaluation points, and the width was partition 2 is 2, plus so on and so forth. So we have square root of 5 next, times 2 plus square root of 9 times 2 is our next rectangle. So these are individual rectangles. Remember, we will have 5 in total. And then we'll have square root of 9 times 7. And we will calculate that up and get an answer. Okay, so before I put the calculations of that, I want to make clear that my x sub k is partition 1. That's the first one. For partition 2, I pulled it from here. This is the width. 2. That's the width came from here. 2. And the last width is 7. Because remember, when we think about this, this is like height times width, okay? Or length times width, however you want to look at it. Because these are actual areas of rectangles. So that's my first rectangle. Height times width, height times width, height times width. This is our function evaluated at a particular point, so that gives us a height. And consistency is, these are our widths, so you can see where those came from, and those are the highlighted portions. So when we calculate this all together, we will get for a total of 37.47 units squared. So check your calculations there. Okay, and we have our new definition, definition 5.16 in your textbook. It's just going to be the interval from a to b of our f of x dx. So this is a similar format. This is called evaluating the integral, where a is your lower limit and b is considered the upper limit. So basically, if we take the limit as our partitions go to 0, so as the width of our rectangles gets smaller and smaller and smaller of this sum, the area of what we've been calculating previously can also be determined by using evaluating an integral. So here's where we're going to evolve a little bit more to using integration methods to be able to evaluate areas under the curve. Okay, with this definition in mind, we're going to work on rewriting something of this format, which is what we've been working with. We've been doing sums where we have the height times the width, and we would add them all up. And we know that if we let the width of these get smaller, we'll have an approximate area. Well, we know that now this is also equal to this integral, and we're going to work with that. But the first step, we're just going to rewrite um, from this format to this format, and then we'll work with some other examples until we start actually evaluating some problems. Alright, so our first example will be to express this limit of sums as a definite integral, so we just want to rewrite it from this format to our integral format. So I'll give you a few minutes to write this problem down and then attempt to do that. Okay, so my reminder is that I want to write it into this format, and first thing I'm going to do is start with my lower limits and upper limits. It told me on the interval from 0 to 4, so A is 0, B is 4. Our F is just 2 pi from the previous, and our W sub k is going to be our X. Okay, so if W sub k is our X, we also have 1 plus W sub k. So what do I put in place of W sub k here? X again, so it's, whoops, so it should be 1 plus X cubed. And then we have delta X sub k is just going to be our dx. That represents our dx. So this is our function, which is this entire piece. And then this is our dx, which is our delta X sub k. So that's just, and our intervals are from 0 to 4. So we're just going to plug that in. So that's just change in notation there. And if that's a little bit confusing, it's okay. This one's a more complicated one, but it's based on the idea that if we have f of x is equal to x squared plus 1, and I ask you to evaluate f at c, we basically replace c everywhere there was an x. So it's kind of that idea right there. So let's look at another. I think we have a definition next. Okay, then next we have two definitions, 5.17 and 5.18. If you'll just take a minute to pause it and write down these definitions. I also did a basic example of this particular one right here just so you can see it with numbers plugged in. Okay, I don't remember if I explained that too much over here, but basically if this lower sum is bigger than the upper sum, we can reverse the order of those and pull a negative out front. Also on this one, it's pretty intuitive. If A and A, if these are the same numbers, when you were to subtract, you're going to get 0. Okay, definition 5.19 is basically the big picture of where we're trying to go. Where we did all those Riemann sums before to get an approximate area under the curve, now we can evaluate integrals to give us that area. And we're going to, a definite integral, we're going to be using this method for the next few problems. So we're going to work with that now.